Hi, welcome to this video on Newton's third law. This is Mr. Kier, and what I have for you here is just a simple picture of someone walking. And this is something we do every single day, but we don't think about it. And the important thing to recognize here is look at the direction of the person is pushing with their foot. They're pushing backwards, in fact, to move forwards, which is really interesting. You have the same phenomenon here when you've got someone that's doing a quick dash. So for example, this runner is just running out of these blocks. And to do so, they have to push backwards in order to go forward. So again, we got this notion of pushing one way and then moving the opposite way. Even swimmers do the same thing. You push onto the wall and then the wall pushes you the opposite way. So you can pick up quite a bit of speed. So all of this is an example of Newton's third law. So what we have here is another example. We've got a skateboard. And in this case, the skateboard is moving upwards along a ramp. In order to do so, you can see here that the boarder had to push backwards on the ground in order to move forwards. So what happened was this backwards push was the force of the skater on the ground. And how did the skater move forward? Well, the ground happened to exert the exact opposite force in the opposite directions. This is the ground force on the skater. And that's the whole idea of third law. You've got two different objects that interact. So in this case, it's the skater and the ground. And whenever these objects interact, the forces are exactly the same, but they act on the opposite direction. So here's a diagram that you guys have in your workbook. Very similar. So again, the first force here, the push, we actually have a name for it. It's called the action force. So F action. So it's the original push. And it's equal to the reaction force. Now, both of these act on different objects, and they're in opposite directions, same size, and they actually happen at the exact same time. So it's not like you have an action force and then the reaction. They happen simultaneously. Very, very important to remember. So in your workbook, this is the definition that I want you to write down. So if you have a chance, pause the video and jot it down. Okay, let's look at it. So the whole idea is, again, two objects are interacting and they exert a force on each other. The exerted force is exactly the same, opposite in direction, and it happens at the same time. And a quick way to remember this is for every action, there's an equal and opposite reaction. So it's in terms of forces. So again, remember that there's equal size, opposite direction, same time, simultaneously is when they happen. Okay, so here's an example that you have. We have a skater, and whenever you skate, in order to move forward, you can see here the skater has to push backwards. So we have a little picture here to show the free body diagram of each object. So this free body diagram is the ice. And what we do to the ice is the skater is pushing on the ice backwards. And on the other side, you have here the resulting reaction force, where the ice is now pushing on the skater, and the skater is beginning to move forward. The ice doesn't move backwards because the ice is so much bigger than the skater. There's so much more mass. Nothing really happens. But the skater is relatively lighter and he or she can quickly accelerate. Let's look at the next example. How about this? How about a hockey puck and hockey stick? Well, like before, we've got two objects. This would be the puck. And what happens is the hockey stick is going to be exerting a force on the puck forward. Then when that happens, you feel a little bit of recoil on the stick, and that recoil is because the puck exerts a force exactly the same size backwards on the stick. So that's why the player will feel the shot. Now, how about jumping? Well, exactly the same thing occurs when we're jumping. So if we're jumping just for fun, when you're playing skip rope, or even when you're playing basketball. So here we have this player, they moved upwards. How do they do that? Well, they exerted a force, they exerted a force downwards on the ground. That'll be my action force. And then the reaction force was the ground pushing the player upwards. Just like before, the difference is in terms of mass will result in the different motion. So the player is very, very small compared to the earth. They move a lot more than the earth does. And the last one, I love this picture. This is the Falcon Heavy. Recently saw this on TV. Elon Musk and SpaceX launched a Tesla Roadster into space. You can see Spaceman up here. And you really have to understand how rockets work. So one thing to remember is the rockets don't actually push on the ground. They don't do that. What happens is the rocket pushes downward on the exhaust gases, and then the exhaust gases push upwards on the rocket. So I have here another rocket, and you can take a look here that I've got the free body diagram for each object. This would be for the gases. So the gases are being pushed, they're produced, and they're being pushed downwards by the rocket at a very, very high speed. And there's a lot of weight associated with that, a lot of force. And then as a result, the exhaust gases are going to be pushing upwards on the rocket and causing the rocket to move upwards. So again, that's it for third law. So the big thing to remember here is that we've got two objects, they're interacting. When one object exerts a force on another, the size of the force is exactly equal to the force exerted back. The only difference is the force that's exerted back is in the opposite direction, and it happens simultaneously. So again, what we have is we've got our action force equal to our reaction force. So for every action, there's an equal but opposite reaction. And that's why I have the negative there. Hope you had fun. Take care.